Thanks for attending. So we're going to do just an overview and a discussion on the management of steel metal bridges in Irish Rail. Irish Rail has obviously a historical stock of bridges back from when the rail was originally built. So we've all selection materials like steel, wrought iron, cast iron, and the maintenance of these program for these is specialist based on railway working. So you have you've all selection materials. You have wrought iron, cast iron, early steel. There's riveted connections, riveted plates, and so on. So any work that we do has to be within the confines of the material, and we also have the problem with running trains and so on. So that obviously any work that we have to do, get done within a railway possession, and also fit within the existing railway envelope and so on. So our maintenance renewal program is based on a cyclic inspection regime, and we have a bridge management system. So the topics here to discuss are the number and the nature of the railway bridges, the bridge management system, the common defects that we see, our design criteria, our repair specification, our paint specification, and I've included a case study on the Boyne Viaduct, which we undertook the work mostly in 2015. Within the Irish Rail network, we've got approximately 5,200 bridges. Approximately 1,000 of those would be wrought iron, steel. There's a few bridges with cast iron elements, mostly decorative now. There would be no load bearing cast iron elements. Most of our metal bridges would be under bridges, which is the road or the river or whatever is under the rail. So that's our under bridge, and our over bridge is where the road mostly would be over the rail. So the few over bridges would have containment issues. They tend to be plate girders, so they would have road restraint issues. So thankfully we have few of those. There are a few cast iron jack arches, but they're on disused lines or abandoned lines, and none of them are on operational railway lines. Within that 1,000 bridges, there's approximately 330 of them troughing bridges, which is the corrugated steel or wrought iron flooring. But 200 additional 200 of those would be plate girders with either solid plate or again corrugated. Some of these. We have what we term principal bridges, which is a span greater than 30 metres, or multiple spans with spans greater than 20 metres. So some of the examples of those would be like the kind of iconic bridges like the Boyne, Thomastown, the Loop Line Bridge, Gormanston, Delvelly, Slatty and Drumsna. So, and again, to make up the 1,000, the remaining would be footbridges or troughing bridges that span abutment to abutment. With troughing would be a very much a railway bridge, very basic design and detailing. In terms of other networks, Irish Rail would have very comparatively few large principal bridges. A colleague of ours worked in Network Rail in Manchester, and within that area alone they have a greater number of bridges, of principal bridges, than Irish Rail would have in the complete network. This is from a catalogue book from 1927, and sorry you can't see the detail you put on. I could, but this bridge here would be like the troughing. So you have the corrugated profile flooring there on top of a cross girder, transverse girder, and spanning onto a main girder. And then over here you'd have plate girder, which troughing. I'm not sure it's troughing. It is troughing as well. Sorry. Yeah. So in the 1920s, 1930s, these catalogue bridges were available and produced by the manufacturers of this steel. So we'd have plenty of examples of Dorman and Long. There. In terms of our principal bridges, our kind of older structures, we'd have again plate girders and lattice. So this bridge here is the bridge over the Dargle at Bray, and 3-span bridge, 60 metres in total. This bridge here is Gormanston Viaduct, and you have 2 original spans and a centre span there that was renewed to match the original. The original was a lattice, and the middle span there is a 1994 truss bridge in steel. So see again, it shows you kind of a mixture of all elements. Just to show some of our newer structures, this is the bridge over the River Shannon, Drumsna, Leitrim or Roscommon, which we haven't. And just there's a reference there. There's a paper on that from Aidan McAdam and Oliver Doyle on the construction of that bridge. That references the Irish Railway Record Society, and there's a full detail of how the bridge was designed and built. And this one is Thomastown Viaduct in Kilkenny, and again, if just the innovative solution there, we cast a concrete deck onto an old wrought iron transverse girder bridge, and again there's a paper on that in the ICE. So in terms of our bridge management system, so we undertake a biannual inspection of all our bridges, and we call that a general engineering inspection. And every 6 years, the same structure gets a principal engineering inspection. And the principal engineering inspection requires a touch inspection of all the load-bearing elements. So we've access requirements there. So machines, scaffolds, and so on. We also undertake a rope access inspection on the large spans, the multi-span principal bridges, and that feeds into our assessment section, which I'll go into now. And all our bridges are rated under design, condition and deterioration, and we call it a DCD score. And obviously the condition and the rate of deterioration are the variables that may change within the period of inspection. So within every 2 years, you have a measurement point from the condition or deterioration, rate of deterioration. So assessments. We have undertaken assessments in the past on a case-by-case basis, primarily to BS 5400. We're trying to develop a more formal process, and we're progressing that from this year. It involves obviously stuff like desk studies, data collection, assessment calculations. As I put here that we're going for level 0 as the Network Rail assessment program. So Network Rail undertake said they would undertake a full assessment on all their structures over an 18-year interval. They commenced that, but they found that time caught up on them. So in terms of the complexity of the assessment, they had a level 1, level 2. So they actually developed the level 0 to allow for a kind of a generic assessment on similar spans, so that like all plate girders up to 20 meters with a depth of a meter and 300 width and so on, they were able to provide a assessment to that level. So that's they're stating that they're getting closer to getting the full completion on 18 years. So we're probably going to start off at that to be maybe not to be too optimistic that we'd get at least the level 0 done within a reasonable time. So, and obviously if you have a failure at level 0, then you progress the detail of that inspection or assessment up to level 1, and then level 2 will be a full finite element assessment. So, and within that, sorry, I wanted to say as well, obviously within an assessment to Eurocodes would be applicable, but we would also know the weight of our rolling stock, the axle loads, so we're able to detail. We will pull back a little bit from the Eurocode requirements. Just a section here on the common defects. Our biggest problem is the water and our corrosion of our bridges, and then the lack of money to maintain them. So we find that we are overly relying on the fact that all bridges were very well built. They put pitch and tar over the steel elements, and that has held for such a length of time. But then, obviously, as deterioration increases, as time goes on and deterioration progresses, you find that the waterproofing is breaking down and so on, so that you get corrosion at the back of bearings and the back of main beams and trimmer beams and bracings and so on at the back of the bridge. The paint systems that were originally employed were lead based, and again, due to lack of investment and the lack of painting, if it wasn't for the red lead, we'd probably be in a lot worse situation. And drainage in the form of drip eyes from the decks, where decks were modified, you may or may not have had a proper drainage system, or drip eye installed to remove the water. So when they were installed, they also needed to be maintained, and we found that if they weren't maintained, it often causes as bad a condition when the water starts running onto main elements and so on. So again, a few photos and things like that. Yeah. So in the 90s, the Belfast Line project there would have been traditional way beam bridges, timber decks on top of steel or wrought iron structures. They took away the timber rail elements and put down flat plates of steel. They were never particularly sealed or drip eyes installed, and then we come along 20-25 years later to find that the tops of flanges and bracings have all been corroded in a perfect way, because we've basically provided water and oxygen and so on to perfect location with all sorts of material dripping down with the crushed ballast. So it all creates an environment where water can sit and progressively corrode the elements. This bridge here on the left, that's the corrugated troughing sections there, sitting onto a main girder. There was never drip eyes installed. There was holes left, so you basically got water spreading out across. And once the water sits in, it starts corroding on the inside of that bottom flange. It's very hard, if at all, to repair it. over here, that's actually a photograph from the Boyne Viaduct. The drip eye at one stage was functional, but once it started to corrode, as it's shown there, the water was basically just dripping onto the bottom flange there and corroding and damaging that area. So one thing we see with painting that we were from the department and so on, when we're looking for funding, is that to some extent they see painting as a cosmetic exercise. That's you're beautifying the bridge. They were made, and we've been trying to point out the fact that it obviously has a more than just a cosmetic function for the bridge. So we've gone off and repaired bridges, and I just put down there to Bray and Ballas there, where we repaired them, and then it took us 5 or 6 years to actually paint them, so they look desperate when they're sitting there unprotected. That's Gormanstown there. That bridge was, we went in to repair it there. We found the painting system had basically completely failed in 20 years, and there was no stripe coating, and for a new deck it was in poor condition after a very short period of time. On the plate girders and troughing bridges, this would be one of our most common defects. The web stiffeners would be maybe 2-3 feet centres on the girders, and once there's water sitting in underneath that stiffener, you get a significant amount of corrosion. And we would go to some bridges and maybe we'd require maybe 30 or 40 of these to be replaced. Depending on how bad the corrosion is, we might try and do a local repair, or sometimes we have to replace the whole thing. So again, that's again, that was one of the bridges with the top flanges, just again water coming down through the top plate. Rivet replacement, we have a bridge gang, and up to the 1970s they were still doing hot rivet replacements, but nowadays we replace rivets with HSFG bolts, grade 10.9. They take a fair bit of effort to remove them and replace them. We allow kind of 1 in 10 to be damaged before we start replacing them. But on a general enough bridge repair, we could do 2,000 or 3,000 rivet replacements on a bridge. I think we did 15,000 rivets replaced on the Boyne, and so it's a kind of system we've developed, a traditional system that we've tried to develop a bit more now. We have to burn the head of the rivet and use a rivet punch to actually force out the rivet. It's a noisy, time-consuming, and difficult enough process to undertake in confined spaces. Just going to show a few photographs of, most of these are from the loop line bridges between Amiens Street and Pierce Street. So again, they're all, most of them are all plate girders with troughing sections on top of them. Very hard to maintain in that they're the busiest location rail-wise, and probably the busiest location road-wise, so it's very hard to get in and get road closures and rail closures to coincide, etc. They've suffered from that effect, and we've tried to do lots of kind of patch up and so on, trying to stop water coming through. But you can see that would be the summary of the general engineering inspection there. So you have multiple areas of leakage, flanges and damage, bridge strikes. I'll show you a bit on bridge strikes, and painting, coatings. The same with this one. You've quite a significant corrosion there on the bottom flange. You've a knife edge on these. So these were just two small repairs that we had to undertake on Amiens Street. A few words of kind of summary on the findings of the general engineering inspection. The common thing is that we've leakage, we've water, and it's causing damage. Same there. That's the bridge in Trinity College, I think. You have two decks buttoned together, water dripping into the drainage goes into a kind of conventional half pipe. That's all blocked up, and then you see what happens then. It's just basic corrosion. In this bridge here, we tried to go in. You can kind of see the patch repairs, bits of welding and bits of plate added in, and it basically needs a proper overhaul. It's not something that you're kind of moving the water along rather than actually repairing the bridge. So it's what does it have there? The effectiveness of these repairs are limited, which is an understatement. Here's where actually the drainage channel itself was completely corroded. So again, we had to replace it out. Rust jacking. For that, we'd have to take out a significant amount of rivets and plate around that damage. And we wouldn't attempt to remove or replace that jack plate at all. I think we'd just plate around it and try and seal it. The seam on the trough. Leakage again, holes and damage to the cross girder. One of our problem again, this is bridge strikes. Custom house key you can see up on the right hand side there. At one stage was our most struck bridge. It's probably always in the top 2 or 3. Vehicles, even though their heights are advertised, etc., the vehicles still collide with our bridges. So you can get tears, as in that example there. You can get scrapes. I know it's not a great photograph, but you get scrapes on that, and then you can get kind of bizarre behaviour with guys travelling. That was a fair job to break the arm off a machine like that. He was travelling fairly fast to do that. So this is just this is the kind of summary of the damage on what was the most struck bottom flange we have. That's the custom house key. It's facing the Collins Street, that side, just outside the custom house. So the construction of that at the mid-span was 7 laminations of single plate, a half-inch plates. The 7 lines of rivets, and the traffic side had only got 5% of the original rivets remaining, and then it decreased across there so the second line had only 10% of the originals left in it. So every time a bridge gets struck like that, the trains are stopped. We're going out to have a look at it. The track people are going to have a look at the track, and all that time people are sitting on a train wondering what we're doing. Like the traffic is stopped, and it can be mayhem around. It can be very difficult actually getting to the bridge, for us. But again, and then we have to go back in and try and replace rivets that have been sheared off like that. So it's not. We've tried to do the advertising and so on. We have to continuously do that and re-educate people on it. But when we are designing new bridges, we have a design standard, an internal standard. We designed to IS, the Eurocode, isn't it? We have geometric designs. We have to meet, so that there's robust curbs and so on. There's heights of handrails and so on that have to be achieved. We also have standard clearances for trains, so there's a dynamic envelope within that has to be provided within any structure to avoid any possibility of collision or so on. We also do kind of like-for-like replacements and designs. This because we have to provide. A lot of the time we're building back within a very confined envelope, and so we would we would have to do a like-for-like replacement. So we would try to install put back what was originally there. I just have a few photographs there. So we'd have to widen out sections and so on. That bridge is quite a low clearance, so we had to widen out a walkway, widen out the deck to provide for a walkway. So we had to use troughing sections, reclaimed troughing sections to make that work. We have a fabrication facility in Mullingar where we do a lot of our own fabrication. So we would do the design in house, or use consultants where required, and for steel bridges we would fabricate them ourselves. We have independent weld testing for that, and we also, when coating for galvanizing and for painting, we have independent checks for the quality on those. So we had to replace a full bridge there so we fabricated that ourselves using troughing sections. This here bottom stiffener. There was a bridge near Connolly Station, and all these, I think that all these stiffeners were corroded. We replaced all those. We tried to put them back in galvanized steel, and that and then when we paint the bridge, then the galvanized steel just receives a sweep blast, and then we paint it as we would the rest of the structure. We fabricated some curved beams there for a bridge in Lochatalia, and again on a like-for-like basis. So it was built basically off the original drawing back in, don't know when, sorry, the 1870s anyway, I think. Yeah. So our repair specification would be to reinstate the structure to its original strength and stiffness. It involves significant works when working with riveted plate structures, lattice girders, and elements that are made up of riveted plates and angles and sections. We replace all our rivets with HSFG bolts. We only replace load-bearing members during a railway possession when there are no train movements, and our preference is to replace plates sections with galvanized material. So when we identify a damaged area, we produce a schedule of repairs, we produce a drawing, we choose our material, which may be high grade or normal grade, but we'd use the J2 minus 20 degree material for the steel. We have our own internal fabrication section, and we have our welding and coating testing inspections, and we do our installations during our railway possession. Again, for our painting specification, I said earlier on there, most of our historic bridges would have been painted on with red lead as a primer. This is provide a significant barrier to corrosion, but it does lead to complexities for painting projects because of its environmental problems and health and safety problems in terms of blasting, burning, or removal of red lead, and then you have to capture it and dispose of it correctly. So you're looking at full encapsulation, correct handling, ventilation systems, and PPE for all operatives and so on. On surface preparation, we'd use SA2.5, or we'd use ST3 in some areas such as stations and around housing, so on. Our systems would have a primer, whether it be a barrier, an inhibitor. Zinc phosphate would be an inhibitor, or we'd have zinc rich as a galvanic barrier. Some of the systems, sorry, there's the last line there. Some of the systems aren't suitable for on-site. We get application. We get comments about using zinc-rich primers on structures. Because of the environment, you have to create a suitable environment to apply the zinc-rich primer. The zinc-rich primer would probably be the best, but it can be difficult to apply to old structures that have corrosion, pitting, or any type of laminations. We would commonly use the N4 system from the network rail standard. I was going to do a little bit on the Boyne Bridge. Sorry. For those who know, the Boyne Bridge would be our largest bridge on our network. The original structure was built in 1855. The 3 steel spans were renewed in the 1930s. The structure would have suffered from a lack of investment and was last painted in the 1980s. The middle span was possibly wasn't painted since the 1930s, and it's difficult to see that it was. We benefited greatly from having an inspection scaffold on the entire structure in 2011, 2012. From that, we were able to itemise and list all the repairs and the defects. So the structure in terms of wasn't too badly deteriorated, but there was works required on the drainage. There were some elements required renewal, and the bearings were all seized and in poor condition. And obviously the bridge needed painting, so the paint system had broken down. To put a detail on that, there was surface water was dripping through the deck and the drip eyes. The drip eyes were corroded and falling asunder. The paint system was effectively broken down, but there was still protection provided by the red lead. The lower elements had some section loss and had suffered from some corrosion, particularly those toe stiffeners, some of the bottom flanges, and the lacers on the lattice girders. Just to go through those photographs, that's the drip eye. Again, I showed you a photograph previously on that, but again, I think I have the number here somewhere, but most of those, if not all of those, had well done their job and were all in a similar condition. This photograph of the lacers between the raking units. So again, that wasn't particularly common, but there were corrosion to that extent on some of those elements. Some of the bottom flanges where water had been dripping down had caused laminations, such as there, and then some of the toe stiffeners had been corroded like that. Again, water sitting in underneath the toe and causing corrosion. And then just as a general thing on the painting, you could see from up above there that the paint system had basically it was beginning to fail. It probably hasn't failed. So again, just to finish out there, the bearings had seized, and they're adding extra stress to the bridge. So what we did was we developed a schedule of works for each of the elements and each of the on each of the spans of the bridge, and we were able to list the renewals required for each of those elements. So we produced drawings and details of the repairs that were required. So that was the repair required for the bottom flange angles. So the bottom flange was made of two back-to-back angles sandwiching a middle web plate. So we had to do that. To replace that, we would have had to remove all the original rivets over a certain length, and during a railway possession, we would take one angle, we'd take the angle out and replace it. So we'd have a good system of marking. We would replace every second rivet during the daytime, while traffic was. While there was still railway traffic, so you could take one rivet out and then we'd replace it with a bolt, and then at night time we would replace out the angle. So there's bracings were replaced, and there's the toe stiffeners when they were that's the detail for those. So you can see that's some of the details there. That's the bottom flange plate replaced. That's in that stiffener, and that's the actual web. The bracing stiffener there too. Our drainage, again, we identified that the drainage system and the drip eyes were defunct. We fabricated these elements here, these kind of down spigots, for want of a better word, and we installed them. I left the bottom of a hanging. Then we came along and we installed from below. Once we had the scaffold in, we had put in all the drip eyes down. So what did we do? We replaced 28 of those in total over the whole span. We replaced all the upper bracings, junction plates here. Retrospectively, this was a poor detail. This before this deck here, during the scaffold was placed, these elements, it forms a flat plate which water sat on and corroded down through the elements. So we had quite a lot of difficult work to replace out those sections and put in those plates. The work was done primarily under a painting contract. So the repair element of it for the three spans, 13, 14 and 15, we'd 8 weeks on the two shorter spans, and we'd 12 weeks on the larger span in the middle. That's again just some details there. At the bottom, angles replaced, and some of the elements there, the the web stiffeners. We replaced a significant number of them, and we trimmed a few just where it was required. A lot of these lacers were replaced with galvanized steel plates. We fabricated quite a lot of those and had them ready to install. So again, some more detail there of bracings, web plates, and so on. Some elements then required kind of bespoke solutions. Originally there were lattice elements here, but there was it transpired to be easier to replace it such in the manner that we did there with flat plate. These are the bearings. They're quite elaborate, but it's kind of common enough, I think, for the time that they formed like this. You had a bottom tray, and then you had a roller section here, and then you had a cast iron element, whether it be a rocker or a guide. This is cast iron, and we knew that the elements or the bearings were defunct and required renewal, but we also had to try and get those out. So we decided we looked at the possibilities of using these holes here to jack the bridge. So this is the process we developed. So we used high tensile bar, and we threaded it through those holes. We designed and fabricated, tested these welding brackets, and we grouted in the high tensile bars, and then we installed our jacks here. And we took 6 weekends to both trial and to remove the original bearings. We replaced them with elastomeric pads and a new bearing base plate. So sorry, can go back. That top element, that cast iron element, obviously we were putting in those bars, and they were going to be highly stressed, but we needed to ensure that that those bars were fully grouted, so that they weren't bending while we were lifting. We designed and fabricated, tested these welding brackets, and we grouted in the high tensile bars, and then we installed our jacks here. And we took 6 weekends to both trial and to remove the original bearings. We replaced them with elastomeric pads and a new bearing base plate. So that top element, that cast iron element, obviously we were putting in those bars, and they were going to be highly stressed, but we needed to ensure that that those bars were fully grouted, so that they weren't bending while we were lifting. So we undertook a trial, and we used a grout from Parex, and we did we made up a simple mock shape, and we did a test, and we, using that grout, we were able to fill that shape successfully. We had to vent it just to remove the any air voids and so on, air pockets, but it worked quite well. It was what we wanted was a fast setting, low flow, and a grout that would fill all the void there. So that was the installation of it. So we took away the edge plate there, we put in our bars, we grouted our bars, and then we put in our jacking plates. So we obviously had to, when we were jacking the bridge, we had to understand and have a fair confidence on what load we were lifting. So we were able to use the original drawings to estimate the weight of the spans. So the two shorter spans we estimated to be about 475 tons, and the middle span about 1,050 tons, and they proved to be quite reasonable estimates. The jacking system we used was from PH Hydraulics. All the jacks were small, from kind of near pancake type jacks. The whole system was all electronic. It was very confident building, because I suppose our experience would be that there was hand pumped jacks and so on in the past, but now it's all computerized. They've all they were able to with sensors be able to show you that you were actually jacking the bridge, that you weren't that the bridge wasn't stuck and so on. So they were able to show displacement for load. A very restrictive access, very tight confined space. So we had the base plate with the elastic bearing was sat there. The jacks were put in place, bridge jacked up, and then we were using tier first. We'd pull out the old bearing carriage there and install the new plates, so it's in there, and the elastic bearing pad in you can't see the pad there, but it's in there. And then unfortunately they painted it like that, but it's painted anyway. But we left the plates in because obviously we felt there'd be significant damage to try and remove them now, and also there was no obvious jacking point before, so in the future we actually have a jacking system. The bridge painting, there's we did a full blast on the base of the bridge, and we did an ST3, a mechanical prep on the girders and the bracing and so on above the track level. It was all tested and so on through the whole process, and as I said before, it's a bit green, but I think it'll fade in time. And that's the completed bridge there. So that's it now. Yeah. All right. Okay.
Did you ever take the opportunity to instrument any of the bridges and see how that correlates with some of the visual defects then?
There are projects going on to do that, and the Boyne has been chosen as one of the projects. It's only in its kind of infancy at the moment, but yeah, that would be the plan, is to use kind of instrumentation and so on to further the assessment process, that you have. You have kind of real-time data and so on, and deflections, and obviously the loading. We know the axle loadings on the trains, so if you're able to get a concise model, you're able to predict a bit more then as well if you have real-time instrumentation on the bridge. Yeah, so that is a project in process at the moment. It's a European funded project.
Thank you for that.
Thank you for your talk, Stephen. One question I would have: you said that you wanted to reinstate the old building of the old bridges to their original strength.
Yeah.
Given some of them are 100 plus years old, do you do any back analysis, and how much fat would you find in it based on modern railway loads?
Again, this work we're trying to we're kind of trying to catch up with ourselves a bit there. Yeah. I suppose what we're saying there is we would know from old drawings that the original thicknesses and so on were like 16 mil or whatever. We would try and put that material back in place, and that is something that we want to do in terms of our assessment program is that we have a kind of a feel for the effect. You know, you get that with arch bridges, people saying, oh, yeah, sure, the bridge, an arch can take anything, you know. So the same kind of mentality does exist there with, you know, the bridge is fine, so sure, put in a 16 mil plate because there was a 16 mil plate there before. Yeah, so it is something that we're behind the mark on a bit at the present, but it's something that we want to develop, and we're hoping that we could develop that in kind of reasonable time, that it's not out there for years. That
Stephen, just thank you for your very interesting talk, and I hope you put right up the case study of the Boyne Bridge again. Those already some paper.
Okay.
It's pretty good. I'm pretty interested in how you dealt with rivets, because it's something I couldn't go over years myself, and you explained the method you derived. So was this where you burnt off the heads and you used a special tool to cure the rivet shank?
Yeah.
Was that something that you developed in-house? Was there something with productivity? I think you mentioned that you had something like 15,000 rivets changed on the Boyne Bridge.
Yeah.
And last question was, you know, off the rivets so closely packed together, is it difficult sometimes to tighten the
It is. They use the tool they use is just a pneumatic rivet punch. It's a horrendous thing to be listening to in the middle of the night. And anywhere we get difficulties with neighbours and so on, understandably. So there is a way of jacking one rivet off the next, and but it's much more time consuming. You still have to do a bit of boring. You obviously still have to bore the head to allow you to push the shank. But we've had that problem in and around Dublin, where people obviously don't want to be listening to you all night banging out six rivets. But the tools to tighten them, we try to. Again, I think they can get in most places, and they use tools with get in and close. We have when we're putting in scaffolds and so on, we always have to try and think that we're not confining ourselves with space and so on. But I think the tools and so on tend to attach to standard drills and so on now as well. So I don't think it's too bad. You don't have big wrenches and things like that, or anything like that. So, and so that the HSFG bolts we've done some testing and so on, that they're as close to the rivet as the rivet can be.
Just interested, to what extent did you have possession of the line for this? Was it closed at night time?
For Drogheda,
yeah.
They keep on calling the project was called the Drogheda Viaduct, but none of us know it as the Boyne Viaduct. There was possessions for the jacking. We were only given 6 weekends or 8 weekends, and we had to use, if we weren't actually doing work, we were doing trials. So we did the trial on each lift, and then otherwise we were working on night to do to replace members. And just as I said, the rivet punching and so on, that was done during the day, so that you'd have, it's clear nights, nights for the people, because again, up in 70 feet up over the Boyne, the noise travels. So yeah, but again, it was done within the very limited closures. I think there was a number of weekends where they stopped the last train on a Friday evening or so on, to allow Friday night to be longer than normal and so on. So,
do you, as a design engineer, do you do a lot more on that sort of programming, or you just leave that to the contractor?
Well, again, we'd have to do a lot of it ourselves because it's in-house gangs, and we'd be very reluctant to let steelwork guys in on our line. Our metal, we call them our metal bridge gangs. Our metal bridge gangs are they're a bit of a cult in the place. Yeah, so yeah. Yeah.
After you say install basically a retrofit solution, how often would you expect it after that?
Within
Yearly or
we don't the bespoke would be, or the general would be every 2 years, and a principal inspection would be every 6 years. We would, if there was requirements otherwise, we would look at. I mean, I'd say we'd look at some bridges every 6 months, and and then if something happens somewhere, we'd be looking at it every week, So there's, but in terms of a standard repair, we would go back within the 2 years to check it again. I'm sure we'd look at it. We wouldn't walk away from it.
All right.
Yeah.
And have you ever come across any issues with fatigue on joints and stuff due to high-speed trains?
That's I suppose we don't significantly, because we don't really have the volume or the speed or the frequency. So any analysis we've ever done on fatigue it's kind of come out on rivets and things like that, and that's probably not the connection's not really going to fail on fatigue, but we don't really have that. I suppose it's something the chairman would love, that we had a problem with frequencies, but we don't. It's quite a. I know there's bridges there 100 years and so on, but you're getting like 4 or 5, 6 traffic a day, Thomastown and so on. There's not the volume that you'd have maybe on bigger networks and more. It might obviously be something that comes if more frequent services and heavier trains are employed, but at present that's not the situation.
Two separate and not related questions. Did you consider any non-mechanically type of bearings? I gathered the bearing you used was a kind of a rocker type. Did you use any of the sliding and patent types? And my other question is, where you had rivets very close together and the corrosion was around the rivet, was there always enough metal left between the old rivets to take the friction grip bolts?
Yeah, if there was any situation where there was, to answer the second question first, we would plate over if we had any issues with material loss between the rivets. We would try and double plate or whatever, top and bottom plates. There were bearings that we installed were elastomeric bearings, but we put back the original translation. We put back the original directions and so on. So from what it was, it's basically the same arrangement as it was previously, but using the elastomeric pads. So there.
Did you consider the non-mechanical ones, any of them?
Yeah, that's what it is.
Yes.
It's elastomeric pad. Yeah, it's not mechanical. Yeah.
Right. Stephen, I was just going to say to you that many times on the boring or the throttle divider, the concern, and probably back to some of the other questions related to the stability or the strength of railway bridges related to the Eurocode saying that it's all to do with deflection and passenger comfort. So it's generally, like from a flexural point of view, span over 1,000. So where they started to fail, I think, was in the cross-girder connection. So the question always was, is the cross-girder simply supported or fixed? I wonder, on the point, were you able to answer that, like from investigation?
Yeah, I think it is, because I think even the way it was constructed, I think it was simply supported in that the main girders were installed, and then the deck was lifted, and the connection between the cross girder, which I think came up in the panel, and the main girders was maybe 8 or 9 bolts. 8 or 12 single bolts. So it looks to be just a shear connection there, rather than you might get some moments in the spacings of the bolts, but not it's not a haunch connection or any yeah, I said you might get it in the bolt group because of the spacing of the bolts, but it doesn't look to be more than a shear connection. So I think it would be that would be the arrangement, yeah, that it's simply supported between the main girders.
Anyone else? Steve, I have one question. Obviously, an important part of managing breach stock is the inspection component. I know the old, before the refurnishment of the Boeing viaduct, there were inspection trolleys. Is there any plan to install the inspection trolleys on the
Yeah,
side?
very good. No, the inspection trolleys we took it's the only bridge we have inspection trolleys on. They were very old, very they wouldn't conform to any health and safety. They were kind of open, open kind of lattice structures hanging off a rail. The rail is okay. We reinstated and repaired the rail, and you can get a coating of paint. The trolleys we've replaced. We have them purchased, and we have access gantries ready to install them. But we actually haven't got around to doing it. We're hoping to do that this year, but during some platform works up in Drogheda itself. So when that is available, we'll install them. They're stainless steel. No, they're aluminium. Sorry, they're aluminium, so they're lighter than what was there previously, and there's a safer access to them and so on. Because as I said previously, you had to climb down off the abutments into this kind of basket, and there was no mechanical propulsion system. Now there'll be a hand winch type of arrangement, so yeah, that's it's kind of in place. Yeah, yeah. No, it just fell off the end of last year's works.